So they don't react. You know that already, huh? First year of that rule. And now we get to the bonds. And I'm going, where the heck did I put that bond slide on? I thought I was so smart the way I did this. I guess not. Hello. Chemical bonds or connections between atoms are done either by sharing the electrons of the valence or by fully transferring one electron from one atom to another atom. If one atom gets an electron and the other one doesn't, we are making salts, like table salt, for example. That's one way of one type of bond. So when we actually put salts into water, into a solution, they separate and become charged molecules, charged atoms. And charged atoms we call ions. And ions are charged so we can have free electrons floating around, so we can create electricity with all that. We can create some interesting things with charged atoms. What do we call this type of bond?
Ionic.
Ionic bond. So we have that type as a main type. So that's a stealing or a giving up an electron, a full transfer. Or then on the opposite, we have a sharing type bond. What's that one called? Covalent. And that is a type of bond when the molecules hold hands. So in solution, they stay together holding hands. So most of the molecules we talk about in the body, they'll become these hand-holding molecules. The covalently bonded molecules in body fluids, the ionically bonded molecules will become salts. They separate out and they have these ions. That's when you drink a Gatorade, you drink electrolyte solution. There's a lot of sugar. And still, that's the idea that you replenish ions in the body because then they hold electrical currents and that does a lot of bonds. What elements can you consider electrolytes? Oh, the sodium, chloride, calcium, potassium, calcium. I forgot. It's coming up here. It's coming up here, except I'm out of order. I don't know why. Oh, I have it in the nutrient chapter. That's where I have it. Yeah, there's like 5 main ones that we have in the body. Iron as well. Okay, then the covalent bond. So we have the covalent bond. We have the ionic bond. When we take a look at the covalent bond, we have to look at one more thing. Those are the sharing of. They hold electrons. So they can either have one electron of each of the 2 atoms sharing, holding hands, or they can have 2 of them holding hands, or even 3 of them. So we can build bonds that are a single bond, a double bond, or even a triple bond. The interesting thing about that is, as long as we have a single bond, it's like one holding each other, they can rotate. Those 2 atoms can rotate around that central axis, because it's only one thread that holds it. If it's more than one, they cannot rotate, they're stuck. And that becomes very interesting when we, for example, talk about the difference between oil and butter. When we talk about, saturated versus unsaturated fats. And then when we talk about trans fats, we'll do that on Wednesday. No, that's not the polar. That's the how many electrons share. If it's a single bond or a double bond or even a triple bond. And so that's different. So let's go to that polar thing though. That's the next stuff. Some bonds can be charged or some can be not. For example, water's hydrogen bonds, except again, water is 2 hydrogens and an oxygen, H2O. The hydrogens, for example, are attached with a charge bond to the oxygen molecule or atom. These molecules have more positive and more negative areas. And the water molecules are very interesting because they use that quality to make their own weak connections between a more positive and a more negative area of a hydrogen with another one, of a water molecule with another one. And that creates its own bond type. They're very, very weak. But we call that bond something. What's that called? A hydrogen bond. So that's just areas of negativity and positivity, like in sort of magnet, like the positive and negative on a magnet, coming together a little bit. But they're also separated real easily. Okay? So we have that, for example, when we make a protein. That's a three-dimensional shaped protein. We need those bonds to hold the shape of that protein, for example. Yeah, see, you can see they don't break through here, so that there's a little bit of connection why this doesn't just break through the water spider. And also you can actually see it if you drop something into the water. The fact that the water goes down like that is because of connected. And so that's a hydrogen bond. In the body, we use it, for example, in the double helix, the DNA double helix. That the bond that makes the rho be the rho in that stair thing or the ladder thing, that's a hydrogen bond. So that's easily unzipped and right put back together. So it's like a flexible type bond. So it's kind of cool. Chemical reactions generally, so that's I think good enough for those bonds. When we then look at chemical reactions, we look at two main things. We look at either building something or destroying something. We're either looking at making bonds or breaking bonds. Making them also, for example, requires for the body to synthesize or build protein. It does that by taking the necessary elements and bonding them together. We call this an anabolic process. So anabolism is building up things. That's why you got anabolic steroids. You don't have catabolic steroids. That would be interesting. Here, Arnold, take some catabolic steroids. In a week, it's this small. But what do we call those? I just said it. What do we call that? The catabolic. So anabolism, you want to know that word, and catabolism. As in building up or breaking down. And so the decomposition is your composting toilet or something. That's the breaking down part. Yes?
You said we need to know which one?
Well, I want you to know the word catabolism as in destructive, as in breaking down stuff, and also, of course, that as in releasing energy. So if you eat food and the glucose comes in and it gets broken down, that's a catabolic process. That releases the energy. When you break bonds, you can make energy. Yeah, so again, it's all about which bond we break how and what we do with it. Have a good time. That was the whole chemistry class. And then the other one, the anabolic, is constructive because we're building things. And then, or also we can call it synthesis because we synthesize stuff. So that's growth, that's repair of tissues. Usually that takes energy. So it's energy absorbing. Learning is probably an anabolic process in the brain. And then we do have also, I didn't mention that in the question, we do have an exchange reaction. And that's when we take, for example, we take a glucose as it comes through the bloodstream and also going to the cell. And right as it gets into the cell, we take an ATP, which is almost like an ATP, very similar. It's a very ubiquitous molecule, we have it a lot. And we clip off a phosphate and put it on the glucose. So we exchange that phosphate and put it on another molecule. And once that glucose is in the cell, then it has an extra phosphate on it. So it's not the same molecule anymore as the glucose molecule. So it stays in the cell now. Plus, the other thing is it lets more glucose come in. But that's a reaction that doesn't really build anything, that doesn't really, break anything down, but it sort of exchanges something to make, like here, tag the glucose so it stays inside the cell. Mostly we'll talk about the other two. That's much more where we're going with our work. Is that the next question?
Yep.
Good. Maybe I'm on top. Then, when we look at these chemical reactions, these building up and these breaking down kind of reactions, drive a reaction forward or do not drive a reaction forward. How do we know how, metabolism, all the correct chemical reactions inside the body, but how do we know which ones do we need more of, which ones less of? We have concentration, that's very, very good. Concentration will drive chemical reactions. But we also have something called enzymes. And enzymes are kind of like, have you ever cooked an egg? Like you turn on the hot plate, then the first is clear, and then it gets white. And that's the albumin protein that gets denatured, gets burned up because it can't handle the heat. And you like to eat that, of course. And so that's sort of like the heat plate, the stove, the oven is like driving forward a chemical reaction, or lots of them. And so that's a great way of driving forward chemical reactions. We just can't really do that in the body. There'll be a lot of stoves in every cell. That wouldn't work out. So in the body, what we do is we use a molecule, or many, many different types of molecules. And these molecules are known as enzymes. So they help in making or breaking bonds. And then we, of course, have other factors. What are the other factors that drive chemical reactions? One of them, says concentration. Temperature, yeah. The hotter it goes, the faster stuff. Particle size of the molecule, yes. Also, the smaller, the faster they move, the more possibility they have to bang into each other. But of course, the one that we focus on the most is going to be the biological catalyst, which is the enzyme. And what it does is, if you have to drive a chemical reaction, you have to break a bond. The bond is the most important thing. So an enzyme, the way it's built, do I have one? The way that an enzyme is built, it takes a molecule. Let me back up. It's like it has a shape to it, and inside the shape it has active sites, and those active sites can grab onto a molecule that has a bond in between and chew away on that bond, or bring two molecules together and sort of hold them there that the bond can get created. And so we can have that stuff happen naturally, but with an enzyme, it is helped along to get it happen. And so what we change in an enzyme, we change the activation energy to let a thing go, like the hot plate, for example. So when we talk about enzymes, we often mention it and saying like an enzyme lowers the activation energy. So that's why they call it like a catalyst. It can create a product with less energy. And so that's the cool thing about an enzyme. And so it's very, very shape-dependent. Structure dictates function. And we'll have more talk about that.
So since catalysts aren't used up in the reaction, what happens to the enzymes that are present?
They are what?
The enzymes. So enzyme is a catalyst that's not
Right.
used up, right?
Right, no, it's not.
So what happens to it once the reaction completes?
Well, it's actually going to be the next one. Enzymes are extremely specific. You can only have one enzyme for one specific type of chemical reaction because they're shape dependent. If you have a glucose and a phosphate, it's exactly that shape that it's going to attach to. Nothing else. And so that's the great thing. When we look at enzymes' names, the name we give enzymes is we describe a process that it does, and then we say ASE at the end. Lipase is for lipids, fatty stuff. Amylase is for sugar. In digestion, we get a lot of this. Because you've got to break down a lot of stuff in digestion.